So by no means what I'm doing during this hour, make 1 hour more, it's not to teach you how to solve boundary value problem. I feel more confident to tell you about distribution of fields, currents, in order to see propagation, diffusion, skin effect, compensating effect, relations with electrical methods. What I'm doing now, it's only to outline what we are doing in order to get results. Because your field work cannot, interpretation of field data cannot be done without this stuff. So now I formulate that. So this is description of electromagnetic field is formulation boundary value problem. Boundary value problem. Now I formulated this problem for stationary field, for transient field, and frequency field. Now let me show you how drastically, I'm sorry, okay, I take this scene. Now how this problem can be drastically simplified if we go to frequency domain. Let us pay attention first equation. In order to emphasize idea, I missed one point here. In general case, we are forced even to formulate initial condition, what was at the beginning. But let us forget about it. We don't need it. Even it's already a complicated problem. Now, we have equation. Equation is heat equation. It's very difficult to solve it for arbitrary field. So in order to simplify problem, we are trying to solve it in frequency domain. Here electrical field depends on coordinates of the point. For example, electrical x, y, z, plus t. So from 4 variables, very difficult. There is derivative with respect to x, y, z, and time. So it's a difficult task. So mathematicians realized that it's much better to go to frequency domain. Let me show how it works. As before, I showed you electrical field, for instance, which is, let me take any component of electrical field, for instance, Ex is equal E naught x times cosine omega t plus minus phase. We don't know amplitude, we don't know phase. So maybe it's possible to present it in much more pleasant form. I demonstrated it. It can be presented as real part, complex amplitude times minus I or plus omega t. We did it already. Let us write plus. We wrote plus. Where A star is equal amplitude times multiplier which shows phase. So let us make one trick which greatly simplifies this equation. Let us take this expression and substitute in this equation and see what would happen. This function depends on the coordinates of the point. You remember I asked you this question. This lovely term depends only on time in a very beautiful form. You will see why it's beautiful. So, step number 1. Let us remembering that any companion Ex equal real part E star E I omega t, substitute this term in left and right part and see what happens. Ready? This function depends on coordinates of the point. Yes. This function is independent. So I substitute here and I have Laplacian, it means derivative, E star E minus omega t, for instance, x, equal gamma mu. What happens here? That's the key point. Do we need to take derivative with respect to time from this term? No. So let us write. What happens with this derivative? How to take derivative g dt from I omega t? I omega, again still I omega t. That's it looks like simple things, but it's a basis of drastical simplification in theory of electromagnetic methods and many others. So let us look what happens here. E star, we don't need to take derivative, it does not depend on time. He minus I omega E minus omega t.
Alex, you're using plus and minus.
Plus, I'm sorry. Here, plus, I'm sorry. Because I'm accustomed to use plus, here, right? Yes, you can write plus, minus, result almost the same. So, yes, so that's derivative with respect to x, y, z. This term does not depend on x, y, t. Can we take it out? We can. So we have E I omega t, Laplacian derivative means star. What happens here? Minus I gamma mu omega. Here we have Ex star, here I omega t. And simple arithmetics disappeared. And something happened. Outstanding simplification. Outstanding. So, let us rewrite this equation. This term depends on time. No. This term depends on time. No. It's a complex amplitude. It contains information amplitude. Amplitude of sinusoidal oscillation depends on time. No, it's a constant. Phase does not depend. So instead of complicated heat equation, we received equation which has name. K square even has K square also have name. Who knows what does K mean? Wave number. Wave number. In literature it's used widely. So let us look in this wave number, square wave number. If we compare these two equations, it's equal I gamma mu omega. In literature, a lot of places where K square wave number appears. Why it's called wave number now, it's not important, because no waves, it's a diffusion, but it has name. So it's complex number I gamma mu omega. But what is important? If we consider sinusoidal oscillations, two great improvement or simplification. Instead of very complicated heat equation, we got equation which not also simple. But what is excellent, it does not contain dependence on time. It's amazingly important result. Now, and this equation has name Helmholtz equation. It was very famous mathematician and physicist, and it's called Helmholtz equation. Helmholtz equation, not with respect to electrical field. It's not electrical field, by no means. In reality, we have generator which creates sinusoidal oscillations, so no dependence on the time. So it's equation with respect to complex amplitude. The same approach is used in seismic and many all other areas of physics, because this equation is much simpler than heat equation or wave equation. Now, that's the reason why we solve forward problem in frequency domain. How to get expression for field? It's written here. When we solve value boundary problem for complex amplitude, please substitute it here and take real part. And then you will get sinusoidal oscillation. Let us check it. So all problems are formulated for complex amplitude. So we have Ex, now X function, time, coordinates of the point and time, it's equal. Real part, how we presented complex amplitude? Amplitude, real amplitude, phase, times I omega t. What is written here? We take real part of this number. What is real part of this number? Real part, A, I, omega t plus phi. Can you help me to find real part of this number? Euler formula. A, real number. Real number, let us take it out. A, real part, E, I, omega t plus phi. What is it? EIX equal cosine x plus I sinus x. So, what in our case x? Omega t plus phi. So, now we got real oscillation. So, boundary value problem is formulated in frequency domain, always for complex amplitude, which contains amplitude and phase. Take real part, and then the result is ready. Then use Fourier transform. We will not discuss Fourier transform. It's too much. Now, let me show one example. How to formulate problem for very classical models of the medium. You came to the field. You assume that you have overburden and host rock. You have dipole. Rho 1, H1, rho 2. You would like to know what is the field here. classical problem, frequency, time, domain. Simply two-layer medium. It could be overburdened, it simply could be layer. Now, let us start. Dipole. How electrical field is directed? But let me show you how I am doing. First of all, I solve this problem in frequency domain. Correct? I choose system of coordinates. Z, R. What is the system coordinate? Z, R, and phi. Huh? Cylindrical. Now, question arises, why did I do it? Very simple. Very simple, because problem possess axial symmetry. You have dipole, and common sense tells you, take any vertical plane, field will be the same. So let us place our source, our transmitter origin. Now we have only one component of electrical field. Only one component of electrical field. So what happens from physical point of view? What do you think? Frequency domain. What do you think? Will we have here current? Yes. What creates current? Two electrical fields. One caused by the primary. How it's directed? Circle. So you will have many, many, many circles. Everywhere. But if you remember our discussion about current ring, it's brave to say that current in this horizontal ring will be caused by only primary electrical fields. Will be also what? Gamma, primary electrical field due to dipole, plus what? This current ring creates magnetic field. It changes with time. Changes with time. Therefore, it creates what? Electrical field. So we have sum of primary and secondary electrical field. Now, from physical point of view, it's clear that whether we have secondary, small or big, always current will flow in this direction. Now, what do you think? What do you think? If I'm close to transmitter, which electrical field will be the most important? Primary or secondary? Primary. That's the basis of systems profiling, about which you heard yesterday or day before yesterday. Far away, secondary will be very important, along with primary, maybe even bigger. Now, since we have one component of the field, let us formulate our boundary value problem. Z less than, no, just a second, everything is correct. That's Z, so Z less than 0, free space. Free space. What would be equation for electrical field? For complex amplitude of electrical field? I gave you Helmholtz equation. Phi plus k square E equals 0. What is the wave number in air? 0. So first of all, the first condition, we have to find electrical field which satisfies very simple, relatively simple equation, almost Laplace equation. Now, we don't need it. Second, when Z between 0 H1 in the layer, we have Helmholtz equation again, K1 square E equals 0. When we have Z greater than H1, we have again Helmholtz equation, or only everywhere I have to put complex amplitude, it's not field, plus K2 square 0. So, where I field, I didn't describe field. Where? At interfaces. So, I write for at surface Z equals 0, Earth surface, where we measure electrical field, let us call E0, E1, E2, not above 1 and 2. So E0 tangential must be equal to 1T. Magnetic field tangential must be equal 1T. 5 conditions. On the boundary between first layer and second layer, we have again right continuity. E1 T equal must be equal to T, and B1 T equal B2 T. What else? Five, 6. When we near source, R goes 0, our field must tend to primary source. Everywhere I have to write complex amplitude. And finally, when we are far away, R goes to infinity. Field, both electrical field, magnetic field, more precisely complex amplitude, must go to 0. And it's a manual, yes? Sorry? 0.6. Let us find when R goes to 0. R not small. R equals square root R square plus V square. Okay. So, I don't even think a little, I don't have any hope that you will completely remember what I'm saying. Idea is very simple. It's a manual. It's a simple for such problem if each step is so well developed that only 1 week training and you will forever know how to solve problem for horizontal layer medium, for cylinder, for sphere. You will be able to write program to do it because there is no any secrets. As you learn how to work with equipment, exactly the same way to do it, this procedure. Now, let us a little discuss more one part. How to solve Helmholtz equation. There is powerful method, separation of variables. It's beautifully corresponds this kind of problem, sound for it. When you perform separation variables, what does it mean, separation variables? A complex amplitude depends on time? No. It depends on two coordinates, R and Z. Let me again only outline. For example, complex amplitude of electrical field depends on coordinate R and Z. Following Bernoulli few centuries ago, mathematicians we are able to present this function as product of two functions. One of them function of distance, another function only Z. That was genius guess. It's simply guess. Nobody knows how this guess was realized. Maybe during sleeping, who knows? But it doesn't matter. It doesn't matter. When we substitute this assumption, which is always correct for horizontal layer medium, in this equation, this complicated Helmholtz equation, partial derivatives, is split in two equations, two ordinary differential equations, one with respect to time, another with respect to p. For example, equation for this function becomes amazingly simple. P, the z squared minus m squared minus k squared, p equals 0, square root. Solution of this equation very well known. It's exponent. Equation for t becomes very famous equation, Bessel equation. Bessel. And its solution are Bessel functions. Again, pure routine. Pure routine. There is no room for thinking at all. Now you're trying to keep tension, but for me it's a routine. There is no place, room for way to think what to do. Everything is described as rules. That's I strongly believe engineer must know, because there is no way to find solution of forward problems. So finally, M, it's called separation of variables, eigenvalue, doesn't matter. So finally, solution is presented as product of this function. And what we have in all our results for horizontal layer medium, the following expression. I only write you general form. Electrical field, for instance, equal integral from 0 to infinity, some function, Bessel function, MR, here. So, I'm sorry, we will do better. Cm EMIZ plus Gm E minus MIZ. And here function Bessel MR Gm. What is what? These coefficients which don't depend on Z and R. What is Mi? M1 equals M squared minus K1 squared. M2 equals square root M squared minus K2 squared. What is it? Bessel function, used extremely widely inside geophysics and outside. Let me show you example behavior of this function. Always not too bad to know. That's I naught mr. Unit, and then decays with distance slowly, but decays. It behaves sinusoid with decaying amplitude. How we find these conditions, coefficients, Tm and Dm? We have this expression for upper layer, for air, for first layer, for second layer. We find these conditions from boundary, these coefficients from boundary conditions, from conditions at these two interfaces. Also, we use condition near source. They are expressed through exponents and contain information about thickness, conductivity, frequency. It's developed in detail. Now, when these expressions are found, what is left? Take Fourier integral, which, if you remember, is electrical field in time domain is equal unit divide 2 pi integral from minus to plus here frequency solution in frequency domain E minus I omega t d omega. This time I missed something specially. What did I miss? Your suffering is going to the end. Mine also. I don't like to give general in this way. So, what I missed? Who knows? Fourier integral is so widely used. We cannot live without it. We use in gravity, magnetic, electromagnetic, seismic, but I missed something. Now, this is result of solution of boundary value problem when our input sinusoidal oscillation with unit amplitude. So, if my generator unit cosine omega t, that is output. That's the solution of the forward problem in the frequency domain. But we would like to get results due to step function, or with ramp time, or due to impulse. What we have to do? I almost gave you all preliminary information. Huh? You remember? Very well. That's more important than solution forward problem from my point. You have your input, step function, time. Your current behaves in this way. How we can what is the meaning Fourier integral? What is it? Sorry? Sorry, please help me.
Represent the time function or the function in time.
Yes. A sum of
Sine and cos.
many of them, or many or few. How many? No, for instance, I have step function. How visualize step function in a using frequency domain language? Sorry? How the contains all frequency. First of all, it's very correct. So you can mentally imagine that instead of your step function, you have infinite number generators which creates frequencies slightly differ from each other, correct? Each neighbor, frequency omega 1, then delta, omega 1 plus delta omega, etc., 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 etc. All frequencies. But one small question. Amplitudes of these generators, the same or not the same? How? How the decay? How? Huh? Very good. That's what I'm asking. So if you have step function, generator keeps constant current, then in some moment instantly disappears, it's the same as if you assume that you have infinite number of continuous sinusoid with amplitude which is equal unit divide omega. So what does it mean? It means you can present your step function as integral. That's the step function. So it's not too bad to feel it. Now, so you found solution for sinusoidal oscillation. Boundary value problem gives you effect due to unit sinusoid. But step function, it's not unit sinusoid, it's many of them with different amplitudes. So how to take care about it here? You have to divide I omega, because it's a sum of sinusoids with different amplitudes. If you're instead of step function, you have excitation in this form. You understand what I'm doing? That's behavior of the current in transmitter. For good or for bad, suppose that's excitation, impulse. But very, very short impulse. What is the spectrum of this impulse? If it's a very, very, sorry?
It's the high frequency signal. Lots of energy in the high frequency end.
Just a second. Let us return back to this case. Previous case. So let us assume we know general feature of solving forward problem for unit sinusoidal oscillation. So our input cosine omega t for any frequency, correct? Now I take step function excitation. What is the spectrum of this? Where is the main energy is concentrated if you speak in frequency language? Low frequency. That's why we use step function. Because low frequency give us more information about deep level. So clear spectrum of step function, unit divide I omega. Clear? So when I say spectrum, it means if I would like to construct step function, I would like to compete with transient methods, I will invent many methods which contains infinite number generators, which simultaneously gives current with different frequencies. I have to take also into account the fact that their amplitude must decrease unit divide omega. Now, what happens if I take, instead of step function, very reasonable method of excitation, this energy at low frequency point, I will take very, very narrow impulse. What is the spectrum approximately of this impulse? Approximately. In other words, huh? Sorry? Does it depend on frequency or not?
The first pulse generates a positive signal, and the second is
Negative, yes.
So you only get the frequency of the escape of that width of the pulse, the period of that pulse, or one on the period of the pulse.
So if I would like to create generators, tell me please what kind of amplitude relation between amplitudes of this generator must be? The same amplitude, different amplitude? The same, the same. So it's almost we're approaching to delta function. So if we solve forward problem in frequency domain and our generator has this form, practically we can, if we are not worried about extremely high frequencies, electrical field will be equal unit divide 2 pi our complex amplitude times I omega t d omega. If we have step function, we have to multiply by spectrum of step function. So that's all difference. Now, let us stop here, because it's enough, 2 hours, it's a very torture for you and me. Boundary problems, no integral for here. Only I would like to emphasize again, we prefer to solve problems in frequency domain, because formulation of the problem in general case, even more complicated that I wrote you down. Equation is difficult, heat equation or wave equation. Then it's many boundary conditions, near source, at infinity, at boundary. Then I didn't write down even initial condition. So it's a very complicated. When we go to frequency domain, first of all, we got Helmholtz equation, which is simple. Second, no initial condition. And then what I wrote, and then shows why we have to do these things. Before I completely finish, again, procedure of obtaining solution through solution for the most classical models which we use in geophysics is straightforward. No room for thinking if you know what to do. Step 1, step 2, step 3, step 4, you can write yourself expression for fields, you can write yourself algorithm for calculation. It's a pure engineering matter. It's not for only mathematician or theoretician. It's wrong. Idea that it has to be divided between engineers and theoreticians does not sound seriously. But after this comment, let's go back to behavior of the fields. Up to now, I describe, except last small problem, I describe behavior of the fields in confined conductors. Now, what is going on in overburden, in host rock? Many common features you see, some very different. So let us start. Let me take simple example. Dipole. Again, our lovely dipole. Now, as I told you, first of all, we will discuss solution in frequency domain. Then we'll go to time domain. Solving boundary value problem, it's simple method, very simple problem. No boundaries, only source, that's it. And conducting medium, conductivity gamma and mu naught. Now, let me introduce system of coordinates. That's theta, that's r. Solution of forward problem shows electrical field, of course, has only one component. It's not again electrical field complex amplitude, is equal I omega mu m mu naught m 4 pi r square sinus theta e a k r unit minus e k r sinus theta. That's if you solve the forward problem as I wrote you before. That's result. Now, again, it's not field. Nobody knows how to measure complex numbers. Voltmeter, if it can measure, it measures real number, volt per meter. Here it's written complex number. So it's a complex amplitude. In order to get electrical field, what we have to do? Take real part from this complex number times I omega t. That's it. This complex number, that's complex number, but real part will be real number. You will see cosine omega t plus phase. Now, there is electrical field as we expected, because horizontal loop all around. Now, there is radial component of magnetic field. It's equal mu naught m 2 pi r cube cosine theta akr. Again the same expression, only cosine theta. So that's the radial component of magnetic field. Even there is one more component of the field, theta. Because if all currents are horizontal, you have to have radial and theta component, be theta. Mu naught m 4 pi r cube sinus theta ekr, here unit minus akr minus k square r square. Oh, I didn't do something unfair. I don't know why I put sinus theta in front, because everywhere I wrote sinus theta in the end. No, he also was. But that's much better. Thank you. So last time I write correctly. So when you see, if you solve this problem, no integrals, no equations, no complicated functions, you have dipole and around uniform medium electrical magnetic field, of course complex amplitude, are expressed through extremely elementary functions. Oh, therefore we can extract a lot from these functions without any computers, even calculator we don't need. Simple function. Now, only let me explain you, and then I start to describe field. What is a K? What is it? Wave number. We know what is K square, I gamma mu omega. Therefore, K equals square root I gamma mu omega. And what is the square root of I? Somebody knows, somebody does not know, doesn't matter. We will find out. It's not, who knows, by the way? Huh? Sorry, can you help me? Why not? Why are you so ready to say no? It's nice when girl tells yes. Now, why are you laughing? Now, what is square root of I? Square root of I. Let me help you. Sorry, I will be happy to get answer. Huh? Sorry?
What degree minus 1? Yeah. The fourth root minus 1.
4? 4 minus?
The fourth root is minus 1.
That's a very good point, but it will go us deeper into the roots and roots. I need something simply. I'm not happy that we have square root. Now you suggest fourth power from minus 1. So please don't suggest me 8 power or 12 power. So give me something simple, please. Let me help you. Huh? It's what? Slowly, please, because I have I'm 17 years United States. I still don't understand what my colleagues are talking about. They don't understand me also. So, but students do understand. That's for sure. It's known. Now, so what is it? No problem. Let me show something which does not have any relation to geophysics. Did we derive? Do we know this formula, how it's called? Euler formula. Correct? So, let us use this formula. Now, I can be presented I pi over 2. Please check me. Sinus pi over 2, 1. Cosine pi over 2, 0. So it's already not too bad. So we are in the right direction. True? Now, therefore, we can write E I pi over 2. What is it? E I pi 4. Quickly back here. E I pi 4 equal cosine pi 4 plus I sinus pi 4. What is the pi over 4? Cosine pi over 4. So we came to simplify. Sorry? Square root of 2. Oh, or 1 over square root of 2. That's the same. So finally we got a very nice expression. Unit plus I. Check me. Now, yes, check me. Square root I. Here what would happen? 1 over 2. Here square unit plus 2I and minus unit. 1, 1 cancel. And we are in good shape. Now, so let me rewrite this wave number. We need it. I did it specially because too often we use it. So can we write, with your permission, it's equal square root of 2, square root gamma mu omega, unit plus I. Is that correct? I blindly wrote everything. So something wrong? It's possible or no? No. Very good. So let us check what is it? Unit plus I. And what would be here? Do you agree if I write in this way? That's the same? Do you remember this quantity? Skin depth. So, it's not simple to get rid of skin depth in equations because it's a very important parameter. So finally, just a second. Now, K equal unit plus I over delta. AKR equal I minus unit R over delta. Understandable? How we call R over delta? Distance over skin depth. Induction number. Again, we came back to induction number. So we have I minus unit times P. P is induction number. Behavior of electromagnetic field essentially depends on, not only, but essentially depends on induction number. Now I would like return back here. Small exercises. We need a little mathematics. I feel it. So, if I increase distance, what happens with electrical field? Why? Well, I start to increase distance from source, from dipole. What happens with this term? So over smaller. What happens with this term? IKR. Here. Larger or smaller? Huge? Yes, it's finally. If it starts to increase, fine. If, then it will be huge. But only if. So, let us look together. EIKR equal, I specially prepare for you this number. So what we have instead of IKR, I minus 1 times induction number, correct? Which depends on R. So EIP, E minus P, where P induction number. So what happens with increasing of separate very exponentially small. What about this term? Magnitude equal 1. Everybody understands? Again, lovely expression. What is the magnitude of this number? Complex numbers take real part square, imaginary, add them together. What is the cosine square x plus sine square x? 1, square root 1. So this term shows you oscillation. This term shows you field decrease. So twice field decreases, not only due to skin depth, due to geometrical factor, unit divide R, geometry, pure geometry, and plus this term. So it's reasonable to be careful with this term. Usually everybody says, oh, R increases plus it goes to infinity, vice versa, it goes to 0. It's natural again, compensating effect, and with increasing field, conducting medium will become smaller. Now, let me only read this equation. What is it? First of all, what is it? You recognize or not? Where? Excellent. This term, I gave you expression yesterday or the day before yesterday, I already don't remember. This field is a radial component of magnetic field caused by current in the loop in free space. That's field only due to current itself. Here there is something else. Why field here differs from field in free space? Because there are other currents. Understand? What is the meaning of this term? Magnetic field in free space, only theta component. So behavior of the field is described by field in free space, time factor, which tells about induced currents, interaction between them. For us, the most important this part, because it contains information about medium. Let me emphasize one fact. When we consider plane wave briefly, I told you that specific case when depth investigation depends only skin depth and change of the field. Here there are two factors, at least. Field decreases unit divide r cube, it could be very strong decrease, plus decay due to currents in conducting medium. Now, first of all, let us pay attention currents. Can we find current density at any point? Because if we would like to understand, we measure field. In order to understand field, we have to know how these generators of the field are distributed. Let us do it. Current density at each point equal conductivity times this coefficient, Ohm's law. All physical laws are valid. Equal I gamma mu omega m 4 pi r squared EKR unit minus EKR. And it's not too bad to write sinus theta, which I missed bravely. Now I would like to ask you a question. What is it? Or let me do different way. What is it? And then we will answer the next question. But you have dipole. At each point there is electrical field. Now, in order to answer this question, let us decrease conductivity of the medium. Ready? Let us decrease conductivity of the medium. What happens with our lovely wave number? When conductivity decreases, resistivity of medium becomes greater. What happens with skin depth? Increases, drastically increases. So, therefore, magnitude of wave number becomes smaller. What happens with this term? Old term. Not only this term, next term also. So let us start from simple case. What happens with this term? If resistivity of the medium becomes greater, Huh? Brackets goes to 1. Good, settle. What happens with this term? Also 1. Good. So we can bravely say, when we start to increase resistivity of the medium, we are here, doesn't matter. We will get this only term. So how to interpret this term? Electrical field due to dipole in free space. In other words, electrical field caused by all inductive electrical field caused by only prime change with time of primary magnetic field. Not too bad. Not too bad. Now, this expression describes complex amplitude of electrical field everywhere at distance 10 miles from dipole and 1 centimeter. Now, when I started to decrease K, finally I took insulator, I got this expression, correct? So this expression is primary electrical field. Now I don't want to consider ideal insulator. I would like to consider real medium. Real medium. Tell me please, is there area in conducting medium where electrical field practically coincides with primary electrical field? Or I have to consider only ideal insulator in order to get this expression. Do you understand my question, or my question is not very clear? Dipole, conducting medium, seawater. Question. In real conducting medium with resistivity 1 ohmmeter, half ohmmeter, 3 ohmmeter, doesn't matter, are there points from somewhere where electrical field coincides with, practically, not exactly, practically with primary electrical field? Huh? Near source, good. So its result not valid only for free space, but for all practical, could be in real conditions, correct? It could be. And what does it mean if you look in this expression? What is the condition when electrical field in the medium practically coincides with primary electrical field? If you look in this simple equation, somebody talk? What is the condition? K times R must be small. Or simply induction number must be small. So we already learned something. We don't know what happens far away so far. But near transmitter, that near does not mean anything. This ratio R over delta, I'm sorry, I didn't write correctly, less than you did. For example, 0.1, 0.2, small number. Now, if this quantity is small, in other words, skin depth is greater than distance where we are looking, studying, then electrical field practically coincides with primary electrical field. I forgot to ask you, primary electrical field depends on conductivity of the medium or not? No, so we know it. We don't care about medium. It's a very important fact. Now, let us look again back. What is it? Due to. Is it correct English? Due to. Yes. Due to, because it's a primary electrical field. So this is the current around transmitter which is due to primary electrical field. Not too bad. Now, before I continue, I eagerly would like to know, maybe I am involved in something very abstract, very unpractical. Maybe this condition, distance over skin depth, takes place at distance 1 micron from dipole. Who cares about it? Let us find out what are the distances where electrical field is practically equal primary electrical field, and current is practically defined primary electrical field. Let us do together. Let me do the following. Let me take R over delta equal 0.2. Understandable? So I consider points where skin depth 5 times greater than distance. We know delta equal what in meters? 10�3 divide 2 pi square root 10 rho over 10, or as you know from approximately with high accuracy, it's equal simply 500, as Ankin yesterday wrote, 10 rho over rho over I'm sorry, rho over m. So now, let us take frequency, let us take resistivity. What is your suggestion for resistivity? 20, 30 ohmmeters, it's okay? Reasonable number? So let us do it. Rho equal 30 ohmmeters. Let us take frequency 100 Hz. You can make correction for high, for low. What happens? 500, here 30 over 100 power 1/2. Is it true? So what is the result? Can you help me? 1/3, 2, what is the distance? Skin depth? 50? 500, 1 over 3, so it will be 250, it's okay? 250? 250 meters. Oh, meters, correct. So, we feel, we are not very wrong, that if distance 5 times smaller than skin depth, then electrical current which arises, induction current, is defined by primary electrical field, that's all. So what is the distance maximum? 50 meters, so it's not 1 micron. So it's not too bad already to feel what is going on around transmitter. Around transmitter, a frequency 100 Hz. Now let me show you completely different example. We will stop there. But this is a process of examination of formulas. Formulas are simple. There are 2 rows. One row, take formula, go to computer, got numbers, that's it. But it's very interesting to investigate, to understand what this Simple formulas tell you what is going on in medium. Then you become reasonably aware about physical foundation of the matter. Let me show you completely different example. Borehole geophysics, induction logic, transmitter, receiver, layer, invasion zone. Who knows what does invasion zone mean? Huh? Good. One. No, I am sure more. More, huh? No? I see. Very often, pressure of the mud, we are talking about oil industry, about deep wells. Very often, pressure of the mud is greater than pressure of